Another important comment that I'd like to make about coherence is that it depends on focus. So the diagram that shows the way different domains fits together, here I've just extracted those domains that lead to algebra, starting in kindergarten. And if you've been able to focus on number and operations, in K5, for example, those three domains represented there, then you have the ability to move on. So, for example, when students go from 5th grade to 6th grade, they're meant to merge their understanding of numbers into a single unified understanding of the number system. Students in, when they first learn about whole numbers, okay, I can add, I can multiply, great, I've got whole numbers. Then they learn about fractions, right? And fractions look completely different from whole numbers. I mean, how do you add whole numbers? How do you add 2 3-digit numbers? Well, maybe, you just use an algorithm, put them one underneath the other, add them up. How do you add fractions? Well, what you do when you add fractions looks completely different from what you do when you add 3-digit whole numbers. There's no wonder that kids would come out of grade 5 thinking, okay, there's whole numbers, there's fractions. Different animals, they live on different planets. But you want them, by the time they get to middle school, to unify their understanding of number so that they know that every number is really just a length, maybe is a point on the number line, that fractions live among whole numbers, or whole numbers live among fractions. They're all the same, they're just numbers. You have a unified understanding of the number system. That's a huge step. That's like an evolutionary or maybe a revolutionary step in understanding. That's students taking a whole bunch of different things and putting them together into a unified concept. And that's the way mathematics works, by the way. Why is it that in elementary school we're studying things that were impossible for anybody to understand 2,000 years ago and were only understood by geniuses? Because mathematics can put things together into unifying concepts. You can't do that if you don't have if you haven't had the focus to get the things that you're putting into unified concept. You really have to understand them well. You can't make that transition when you go from 5th to 6th grade if you don't have a solid grasp of whole number and their operations, fractions and their operations. And so focus, giving you the time to really do a thorough job in the early grade levels, leads to being able to tell that coherent story as you move from one thing to the next. The same applies to the algebraic aspect of number work. The reason we separated out this sort of operations and algebraic thinking from number and operations in base 10 was to try and sort of separate out the dual nature of the work that you're doing with numbers in elementary school. Partly you're just learning about numbers, how the base 10 system works, how you add, subtract, multiply, and divide them, number sense, a sense of computation. That's the sort of number and operations in base 10 side of things. But there's another important thing you're doing, which is you're seeing how the operations work. You're seeing that you can decompose numbers in different ways, add them up in different ways. You'll see that you can change the order in which you add things and it doesn't change the answer. That's the operations and algebraic thinking side. And that's what leads to the expressions and equations work in middle school, where you start working with algebraic expressions. And then those two grand threads flow together into the vast sea of algebra in high school. So let me say a little bit about what we mean by rigor, and I think what I'll do is try and stop, say, 10 minutes to 5, and allow plenty of time for questions, because I'm sure you've all got some. So rigor to a mathematician means something a little bit different from what I've gotten here. Right? For the mathematicians in the audience, rigor means logical, rigorous proof. We use the word rigor here in the same sense you would use it when you're talking about a rigorous training regime for a sport. Namely, it has to be balanced. You don't just exercise one muscle. So rigor means balancing conceptual understanding, procedural fluency, and applications of mathematics. So for example, there are many standards that call explicitly for conceptual understanding. I've just listed a few cluster headings here that use that word understand. When we were writing the standards, that was there was some feedback that said, well, you can't use that word because we don't know how to assess it. And good point. It's hard to assess. I'm not sure it's impossible, and we won't find out if we don't try. But we thought what we were writing was not a document for assessment, which not an assessment framework directly, but we thought we were writing a document that describes what we want our children to understand and be able to do, or to know and be able to do. And, I mean, ask any parent, well, what do you want? A kid who understands what they're doing or a kid who doesn't? They're not going to say, oh, I'll take the one who doesn't, right? I mean, so it seems like understanding was something we want, even if it's hard for us to find out how to assess it. One of the huge battles over mathematics education that I think has stalled our progress for the last 20 or maybe 200 years is this battle between, should you just we want, there are the people saying we just want kids to know the facts, basic facts, just be able to do it. I want to be able to add some fact, right? And then there are the people saying, no, they should understand what they're doing, they should really have a sense of the beauty of the subject, and so on. And there's this sort of false dichotomy that we've been locked within for years. Of course, it's not balanced to just concentrate on one or the other. What we want is both in some balanced, integrated way. And so there are, in addition to these standards that require conceptual understanding, there are also plenty of standards that require procedural fluency. Kids should know their addition facts, they should know their times tables, they should be able to use standard algorithm for the main operations of arithmetic. So there are various fluency standards throughout the standards as well. And then you also want, what's the point of learning mathematics? I think most students probably, often don't see a point. And the point ultimately is you want to produce students who can use their mathematical knowledge. So there are also standards that demand that. In particular, in high school, there's a standard for mathematical practice, which says students should be able to use their mathematics, says model with mathematics. And then in the high school standards, there's a whole conceptual category called modeling, and the standards for that category are distributed throughout the other categories. There's a little sort of modeling star that indicates which ones those are. And those all indicate, these are standards which are particularly focused on teaching students to be able to use the mathematics that they've learned. Okay, so I think I'll just mention a few resources and then stop there, because I feel like I've talked long enough, and you might have questions. A lot of what I've said, these slides are based on a talk I gave at the International Congress of Mathematics Education in Korea this summer. You can find that talk at the second resource listed here, which is my blog, commoncoretools.me, which is a resource, has lots of things on it that will help you learn about the standards. And it also has forums where you can ask questions about the standards. One particular project, and you can find the materials for this at this blog, or also you can find it at the Institute for Mathematics and Education website, is the Progressions Project. I mentioned very briefly that the way the standards were written was we asked the working team to write progressions, narrative descriptions of how a particular domain evolves over time. Those were the foundational documents for the standards. The standards were then sliced out of those, so to speak. But the progressions documents themselves did not keep up with the editing of the standard. And so we now have a project to produce final versions of those. So you can go and read, 15 pages on fractions, or 40 pages on number and operations in base 10. And then the Illustrated Mathematics project, which I talked a little bit to some graduate students about this morning, is a really, I think maybe for me, the most exciting project.